Okay guys, how are you? I hope all is fine, and I'm just going to share another thesis which was actually represented by Gavan Kumar and Anandana Krishan, and the thesis is about aerodynamic performance of low to moderate aspect ratio wings at low Reynolds numbers, and was submitted in partial fulfillment of the requirements for the degree of Master of Science in Aerospace Engineering in the Graduate College of University of Illinois at Urbana 2012. Urbana, I believe it's, and that as the advisor was Professor Michael Seelig, and because of that, actually, this whole thesis was actually because of his support and help. The Gavan Kumar Krishan just completed this whole thesis, and I'm very grateful actually just putting it on the Google just so that we can share it with the help of actually notes. And I have actually taken some of the extract of this whole thesis in my first part of the video, because it's quite a long thesis. If you want to have the linkage, we can actually share it with you guys as well, but sharing just the part which is very important just as a beginning, because the rest of the thesis is dependent upon the concepts which have not been yet covered by us in aerodynamics engineering channel. So that is why we're just going to cover only those parts which have already been covered by us in aerodynamic performance or aerodynamic engineering. So by low Reynolds numbers aerodynamics, which is the fundamentals of fluid dynamics, fundamentals of fluid dynamics, let's see. Prior to describing the characteristics of low Reynolds numbers aerodynamics, it is imperative to understand the fundamentals of fluid dynamics over a given airfoil or flat plate. Okay, the Reynolds numbers of a fluid flow is a non-dimensional value that characterizes the ratio of magnitudes of inertial and viscous force acting on the fluid, and is given by Re, which is rho, velocity, which is infinity, and it's L by mu. This is the Reynolds numbers relationship when the viscous force are acting on the fluid. So this is how we're going to explain first of all the fundamentals of fluid dynamics, where rho is the density of the fluid, L is the characteristics length, rho is the density, L is the characteristics length, and mu is the dynamic viscosity, that is mu. So that is how you're going to show it. So this is the just the beginning. It has the intro, but I have actually skipped that intro just for the sake of actually the text that has to be written over the paper, just for the sake of actually just first of all developing what we have learned already in our earlier videos in a separate channel. So let's see in the next page when it has been turned over. Dynamic viscosity needed to calculate Reynolds numbers in temperature dependent and can be calculated using Sutherland's viscosity law as shown in mu by mu naught, which is just the whole relationship. So where mu naught is the reference dynamic viscosity at the reference temperature T naught, and S is a constant defined as the Sutherland temperature. For the wind tunnel experiments performed in this research, Sutherland viscosity law was used to determine the test section dynamic viscosity. In flows with Re greater than 1, the inertial forces of a fluid are much larger than its viscous forces. This characteristic allows the use of an viscid fluid assumption, where the fluid's viscous effects are discarded. However, as alluded to by Becherus with the introduction of a stationary body, that is airfoil or flat slip or flat plate, and its associated no slip condition, the inviscid flow assumption is rendered inappropriate for most cases. Okay, the no slip condition states that the initial velocity of the fluid flow is 0 as the solid boundary of a stationary body is approached. Okay, as a result, there exists the thin region close to the boundary of the body where the initial velocity of the flow of retarded is retarded with respect to the fluid as a whole. This region of fluid is called the boundary layer. We have learned in our videos and was initially discovered by Ludwig Prandtl in 1904. The boundary layer of a fluid is divided into three separate regions: the transition region, okay, and an unsteady turbulent region, as shown in the figures, which we're going to actually show in the next page. With an oncoming steady flow, a laminar boundary layer initially grows from the forward stagnation point of a body, airfoil, or flat plate. As the flow proceeds farther downstream, there exists a transition point that is dependent on the local Reynolds number of the flow and the surface quality of the body. As stated by Koche and Chow, downstream of this critical Reynolds numbers, the boundary layer becomes unstable, and any small disturbances in the flow results in a turbulent balanced boundary layer forming. The relationship between critical Reynolds numbers and the smoothness of the body demonstrated by Osborne Reynolds in 1883. So with the low aspect ratio wings, that is normally the part or the title of this thesis. Just giving a brief intro on this. For low aspect ratio LAR wings, AR is less than and equal to 2. The lifting line concept becomes of limited value as the local airfoil section characteristics cannot be separated from the wing as an entirety, which is low aspect ratio wings have two main sources of lift, a linear and non-linear source. The linear lift is derived from the bound vortex flow associated with circulation around the wing. The non-linear lift is associated with strong wingtip vortices that emanate from low aspect ratio wings, and these strong vortices induce strong cross flow velocities on the upper surface of the wing, resulting in a decrease in pressure. So this is how it has been shown with the potential flow sharp edge. This is and potential flow with the round edge. This is the shape, and also with the separated flow with a sharp edge. Obviously this is the spiral vortex, and this is normally the attachment point. That is a separated flow, but obviously it has been attached and with two different type of the body, but the flow is there. And this is the low aspect ratio wings. So that means at low aspect ratio, the line concept is of limited value, because at that point the local airfoil section characteristics which cannot be separated from the wing as an entirely. Okay, so low aspect ratio wings have two main sources of lift. First of all, though obviously there is a source of lift even at a low aspect ratio, a linear and a non-linear source. The linear lift is derived from the bound vortex flow associated with circulation around the wing. The non-linear lift is associated with strong wingtip vortices that emanate from LAR wings. These strong vortices induce strong cross-flow velocities on the upper surface of the wing, resulting in a decrease in pressure. So this is how you're going to share the low aspect ratio wings. And this is just the introductory. I'm going to actually share, obviously, especially in this channel, all the videos that would be related to thesis. And obviously, we are dealing right now the aerodynamics performance of low to moderate aspect ratio wings at low Reynolds numbers. So when we see that we have covered enough in our actually aerodynamics or engineering channel, that may help us to actually read, not just to read out the thesis, but eventually able to translate it and explain it with solid actually understanding. That is the main point of actually producing these videos. We can actually just screen share or even with the screen cam or screen recorder, you can actually show this whole bit of the thesis, and you can actually check in our other video or on the channel Nota Bene Tech on Tube. We were following the same sort of the pattern, but the reason to jot it down all the details is just to keep it with the need of the thesis, what the thesis want us to share with us, the details, and also we can understand, grab and apply, and also we can help you guys as a viewer to understand what the point of thesis. So at this point, aerodynamic performance of low to moderate aspect ratios at low Reynolds numbers, as has been given by Kevin Kumar, has actually, I'm going to end it right now, because it just given us the fundamentals of fluid dynamics, which we have discussed mostly in our video, but probably we're going to rediscuss it in our videos as well, just to give a refresh of understanding. And later on we're going to actually just continue with this thesis, so that obviously we can complete the thesis, which is around about 250 odd pages, but we're going to extract the main points, what is being actually conveyed through this thesis. It is normally a 1 point explanation, but the explanation has already been actually supported by the photographs, some of the photos already been in the thesis, but it's quite a bit with the graphs and the data, and that is why we want to actually correlate that all information with all the concepts that need to be actually conveyed through our another channel. So I hope we'll be able to actually complete this thesis as soon as possible, when we're able to actually complete the aerodynamics courses or aerodynamics, some of the concepts that we are working. That is quite a lengthy process, that is quite a lengthy procedure, obviously for our engineering perspective, but for that reason, or for actually complete for the engineering channel, but for that reason we're going to wait till we have that foundation. We're going to just come back on this and we can complete this thesis. So I hope with the aspect and with this low to moderate aspect ratio wings at low Reynolds numbers, what is the impact? That is what we want to have. What was the impact on the performance of the wing? Just to give, we have driven the Reynolds equation, and the potential flow, obviously at low aspect ratio, the potential flow with the sharp edge is this one, the potential flow round edge is this one, and separated flow sharp edge is this one, which is the attachment of this point. So this is how you're going to explain right away with the help of some of the basic example, that at low aspect ratio wings, which is AR is less than or equal to 2, what you can do, you have the potential flow with round edge and you have the separated flow with the sharp edge that is in front of you. Okay, so potential flow with the sharp edge is like this, and round edge is this, and with spiral edge it is separated flow, but obviously there is a sharp edge over here with an attachment. So this is how it's been explained. So that is mean with the more information, obviously there is a lift in the wing, then because of the linear lift and the non-linear lift. The linear lift is derived from the bound vortex flow associated with circulation around the wing. Okay, and the non-linear lift is associated with strong wingtip vortices that emanate from ALR wings. Okay, these are the two different concepts. These strong vortices induce strong catch flow velocities on the upper surface of the wing, resulting in a decrease in pressure. This is how it has been explained, and I hope it is quite a bit, frankly speaking, very good enough of the concepts that have been delivered. So with the help of these, I hope we'll be able to actually explain the other remaining parts, and I hope that we'll be able to actually get maximum of that. So with the help of this, I'll able to end up my, what you can say, the video. about the introductory video about this thesis, and later on to be covered with our other concepts in line. So I hope you will able to actually keep following, or even at any moment of time in future, and hope to actually reciprocate with the same. So till then, take care and have a nice day.